Hello, everybody, and welcome to the fourth of a five-class series on the introduction of anesthesia and mechanical ventilation. In this class, I shall be speaking to you about the history of mechanical ventilation and a few parameters that are involved during mechanical ventilation. The class module covers the history, certain definitions, and the parameters involved while mechanically ventilating a patient. Most of you would have been wondering what a ventilator is all about. While doing surgery, the patient may sometimes need a mechanical ventilator in order to deliver the anesthetic gases as well as oxygen to the patient. When the patient is put on the ventilator in the ICU, the patient may require the ventilator to support his or her breathing. A mechanical ventilator is a machine that generates a continuous flow of gas to the patient airway. It is controlled and it supports the ventilatory function of the respiratory system, and it improves the oxygenation by giving high oxygen content and a positive pressure. Ventilators are classified to different manners. Robert Chatburn initially classified ventilators into negative pressure ventilators and positive pressure ventilators. This is in the manner by which they support ventilation. Negative pressure ventilation is a manner by which the patient is kept in a box, that is, the thorax of the patient is kept in a box, and negative pressure is applied over the chest and around the chest, the thorax. Here you can see a piston is pulled up, which causes a negative atmosphere over the patient's thorax. This helps to suck in the air from the atmosphere because air is at a higher pressure in the atmosphere and there's a lower pressure in the patient's lungs. Positive pressure ventilation is a method by which air is forced into the lungs. Air from a higher pressure is drawn towards air which has a lower pressure inside the lungs. So if you can see, there's a positive pressure driven by the piston and a positive pressure is transferred to the patient's lungs. Negative pressure ventilator exerts a negative pressure on the external chest. This decreases the intrathoracic pressure during inspiration and allows air to flow into the lungs, filling its volume. This is similar to what happens while a patient is spontaneously breathing. The negative pressure ventilation is used gently in chronic respiratory failure patients or patients who are suffering from poliomyelitis, muscular dystrophy, amyotrophic lateral sclerosis, or myasthenia gravis. Some of you must have heard about the iron lung. This was introduced in the early days by Philip Drinker and was also known as a Drinker respirator. The person who assisted him was Louis Agassiz Shaw Jr., and they were professors of industrial hygiene in the Harvard School of Public Health. This machine is powered by an electric motor with air pumps from two vacuum cleaners. The air pumps change the pressure inside a rectangular airtight metal box. Therefore, it pulls the air in and outside the lungs. So what you can see here is the Emerson iron lung. Later, what came was the biphasic cuirass ventilation. This was a process by which the patient has to wear an upper body shell or cuirass, and it was named after the body armor worn by medieval soldiers. The ventilation is biphasic because the cuirass is attached to a pump which controls both the inspiratory and expiratory phases of the respiratory cycle. However, the biphasic cuirass ventilation had its disadvantages. This was because it was complex and cumbersome, and it was difficult to transport this ventilator. In case the patient had an emergency, it was difficult to access the patient, and it was also claustrophobic. Now, let us understand when positive pressure ventilation was introduced. Andreas Vesalius in 1555 first described the positive pressure ventilation, but it took 400 years to apply his concept to patient care. This was during the polio epidemic of 1955, when assisted ventilation had a very high demand, and this outgrew the supply of negative pressure tank ventilators known as iron lungs. In Sweden, all the medical schools were shut down, and medical students worked in 8-hour shifts as human ventilators, manually inflating the lungs of the afflicted patient. The invasive ventilation was first used at Massachusetts General Hospital in 1955. And that was when the era of positive pressure mechanical ventilation began. And the same era of intensive care medicine was started. What you can see here is a picture of the polio epidemic that occurred in 1950, and the nurses tending to all the patients whose breathing has been assisted by the iron lung. Now, there are a few definitions that one must know while dealing with a patient who's undergoing mechanical ventilation. These are the peak airway pressure, the total inspiratory time, the end expiratory pressure, the mean airway pressure, the peak airway pressure, the plateau pressure. You will also have to know the basic equation for gas flow, the compliance of the patient's lungs, the resistance of a patient's lungs, the time constant, and the critical volume. Now, peak airway pressure. This is the highest pressure that is attained during the inspiratory phase of the patient. This will depend on the thoracic wall compliance. The lung thoracic wall compliance means the extent to which the thoracic wall and the lung can expand while the patient takes a deep breath. The peak inspiratory pressure also depends on the airway resistance, the delivered tidal volume, the inspiratory flow rate, the end expiratory pressure, and the work of breathing. Airway resistance is the resistance offered by the airway to the flow of air into the patient while the patient is taking a deep breath or during inspiration. The delivered tidal volume is the amount of volume of air or gas that enters the patient and is achieved by the patient during mechanical ventilation. The inspiratory flow rate is the amount of volume per unit time that the patient is getting administered. It is measured in liters per minute. There is something known as an end expiratory pressure. This is the amount of pressure required to keep the air sacs inside your lungs patent. Patent means to remain in a ballooned up position. We shall look through the following definitions as the class goes by. Total inspiratory time is constituted by the inspiratory time and the inspiratory pause time. The inspiratory time is the time during which the tidal volume is delivered. The inspiratory pause time is the time during which the gas is allowed to distribute from the upper airways to the lower airways. So the end expiratory pressure is the pressure maintained in the lungs during the expiratory phase. If it is allowed to drop the atmospheric pressure, it is known as ZEEP or ZEEP, which is zero end expiratory pressure. A negative end expiratory pressure is not used anymore, whereas a positive end expiratory pressure is used commonly. The mean airway pressure is the pressure during one air respiratory cycle. The peak airway pressure is the maximum airway pressure during any time during inflation. A plateau pressure is measured when the tidal inflation volume is held in the lungs after the end of inflation, preventing the lungs from deflating. The end expiratory pressure is set by the presence or absence of any special devices. So when it comes to the physics of understanding the gas flow into the patient during positive pressure ventilation, there is a term known as the total pressure gradient. This is given by the equation elastance into volume plus the resistance into flow. It can also be understood by the positive pressure generated by the ventilator minus the negative pleural pressure generated by the inspiratory muscles. So this is the commonly used graph in trying to understand what are the pressure changes that occur when a patient is mechanically ventilated. The pressure is plotted over time. The pressure reaches a peak, after which there is a plateau, and during the end of inspiration, there is something known as the end expiratory pressure. Now, what is work of breathing? Work is performed whenever an applied force causes a displacement of any mass. It is given by the equation work is equal to mean pressure into volume change, which is the area under the pressure volume curve. Work is done by overcoming the compliance of the lung and the thoracic cage, the resistance of the airways, and the frictional resistance of tissues and inertia. Compliance can be understood as the ease of distension of the alveoli. It can be given by the equation compliance is equal to change in volume divided by change in pressure. The elastance is the ability of the lung parenchyma to return to its original form after being stretched. It is given by the equation elastance is equal to change in pressure divided by change in volume. Now the compliance can be divided into two types. It can be understood as the static compliance and the dynamic compliance. A static compliance is given by the equation tidal volume divided by plateau pressure minus the positive end expiratory pressure. This value is affected by lung and chest wall compliance. A dynamic compliance is given by the equation tidal volume divided by peak pressure minus the positive end expiratory pressure. This value is affected by airway resistance and static compliance. Static compliance can be understood as the amount that is measured when the flow of air has ceased, such as breath holding or during apnea. It can be given by the equation static compliance is equal to the change in volume of liters divided by the change in pressure in centimeters of water, which can be also be read as kilopascals. Now the compliance of lungs is 0.2 liters per centimeter of water, and the compliance of the thoracic wall is 0.2 liters per centimeter of water. So let us understand how or what thoracic compliance is constituted by. Therefore, a volume change of 0.2 liters in the thorax is obtained by a pressure of 1 centimeter of water exerted against the lungs in conjunction with the pressure of 1 centimeter of water against the thoracic wall, giving a total thoracic compliance of 0.1 liter per centimeter of water. Now that we have understood what compliance is, let us understand what resistance is. It is a measure of opposition of flow which must be overcome to move a volume of air through the patient's conducting airways in a unit of time. Now flow rate is given by the equation flow rate is equal to tidal volume divided by inspiratory time and can be measured in liters per second. Now resistance can be given by the equation resistance is equal to peak pressure minus plateau pressure divided by flow rate and is measured in the units centimeter of water per liter per second. The normal resistance is 0.2 to 2.4 centimeter of water per liter per second. Time constant is a phenomenon whereby a given percentage of passively exhaled breath of air will require a constant amount of time to be exhaled regardless of the starting volume, that is with constant lung mechanics. Time constant is given by the equation resistance into compliance. What is critical volume? So the alveoli are tiny sacs which are present inside the lungs. This behaves as an elastic semisphere and obeys the physics of an equation known as the Laplace equation. Here, the distending intra-alveolar pressure is given by the equation 2 into the surface tension of air-liquid interface divided by the radius of the alveolus. Now that we have understood the various parameters and definitions that are employed while trying to inflate the patient's lungs in the ICU, we shall now look at the different modes of ventilation in the next class. Thank you for watching this class.